My name is Miguel Secillano. I'm a sixth grade student and I intend to be a computer scientist. Over 2 years ago, I started working with a technology mentor where most of our effort has been in computer programming. Since then, I have learned languages like Scratch, HTML, CSS, JavaScript, Visual Basic, C Sharp, C, and Python. This past school year, I have taken 2 virtual courses in computer science from Harvard University and have received certification in C, Python, HTML, and web development. My project is about throwing darts to derive the value of pi using a Monte Carlo computer simulation. About a year ago, I read a paper by A. Jones entitled Estimating Pi with Monte Carlo's Simulated Dart Throwing. It intrigued me, so I decided to use the concept for my science fair project. The diagram shows a circle perfectly fitted into a square. Not going too deep into the algebra, the result is that pi is equal to 4 times the area of the circle divided by the area of the square. How dependent are the results of a computer simulation based on the quality of computer-generated pseudorandom numbers was the question I have been considering. My hypothesis is if we use lower quality computer-generated pseudorandom numbers instead of pseudorandom numbers of higher quality, then the random numbers may be able to be used in many computer simulations and will provide acceptable results using significantly less computer resources. Let me explain the procedure I used to develop the computer simulation program. Now, referring to the diagram, first I create 2 random numbers that represent the x and y coordinates of a single dart throw. Then I paint it red if it's inside the circle, black if it's outside. Now I repeat those steps 50,000 times. Next, I divide the number of darts in the circle by the total number of darts in the square. Then, I multiply the answer by 4, and as you now know, the result of that is the simulated value of pi. Now behind the scenes, let me tell you about my computer program. I've shown you a little snippet of my code. In total, I wrote 258 lines of JavaScript code. The output from the program was fed into Excel to do analysis. Let me show you a video sample of my computer simulation program running in slow motion. See the darts? Now here is what the results look like after 50,000 darts. The good random number generator filled up the space, but the bad random number generator didn't do a good job. It just made lines on the screen. This slide shows some of the early charts that I created. I believe these next 2 charts tell the whole story of what was learned. The first chart, showing the number of darts, shows the amount of computer resource usage, which is proportional to the number of darts. After running 2,000 trials for each of the random number generators, my algorithm for the good random number generator proved to use the least resources, as much as 42% less than the bad random number generator. This next chart shows the quality of the results of the simulated value of pi. The good random number generator estimated the value of pi to be 3.141552, which is only 0.0013% deviation from the actual value of pi. Not bad. It is hard to believe the amount of random numbers that had to be generated to produce the data for this project. I threw about 4 billion darts. Each needed 2 random numbers for the x and y coordinates, thus bringing the total number of random numbers generated to nearly 8 billion. This explains why my computer needed to run over a 2-night period to complete the 6,000 trials of the simulation. In conclusion, although the lower quality of the random number generator had a percent deviation from pi 2.5 times larger than the higher quality generator, the fact that the absolute value of the deviation was so small, it generally will not have an impact on the results of simulations. However, the length of time to generate the value of pi was 42% longer. In the future, I plan to conduct additional trials to force the simulation to use the same amount of resources to produce the value of pi, then determine the quality of the derived values. The history of computer simulations goes back to World War II. In the early 1940s, 2 mathematicians, John von Neumann and Stanislaw Ulam, were having problems with the behavior of the neutron. Real-life experimentation was too expensive, and the problem was too complicated for mathematical analysis. So, a computer simulation was used and proved to be successful. Computer simulations were not accepted early on because of the significant amount of computer resources necessary. Computers of the 1940s were very slow. By the mid-1960s, computer speed has increased significantly, and computer simulations were becoming an important tool to the scientific community. More emphasis was being placed on improving the quality of pseudorandom number generation. This was okay because computer speed has been growing at an enormous pace, doubling every 2 years, Moore's law. This trend is now significantly slowing. My science fair project was intended to see if using lower quality pseudorandom numbers could be used for thousands of applications. The results of this project suggest that lower quality pseudorandom numbers can be used in many simulations, and thus requiring significantly fewer computer resources. Thank you for watching. This project has reinforced my excitement about computer simulations, and I am very likely to add more to the dozens I have made.